check the link. There it is. Okay, that should be good. And where's Discord gone again? There we go. So the link for the today's live stream, if you can't make it into the Discord stream, or if you want to see it later, that's the link for today's lecture. Welcome everybody again. I'll hold it. I'm just gonna need to talk to somebody in the consultation room. Let me see if Alex is there. Hey Alex, what's up? Do you need access? I'm going to be talking in the classroom rather than the consultations. You're on mute if that helps. Okay, I'm going to kick off the class. I'll be back there. So we'll try that again. Sorry about that. So where are we? Well, we're in week 2, and last week we talked about some base power, energy, material properties that lead to resistance and how resistance changes with temperature. I need to do a few more pieces of the tutorial that we started last week, so we're going to do some of that today. And the main things I want to do today are talking about series and parallel circuits and combination circuits, things called Kirchhoff's voltage law and Kirchhoff's current law, and probably do some background on linear algebra. We probably won't get to mesh analysis, but let's see how we go. So that's the overview. As far as I'm concerned, we've covered the items in grey in the left column, so voltage, current, resistance, power, energy. We've covered passive sign convention and Ohm, talked about resistance from resistivity and shape, and resistance change with temperature. What I'll do once I think we're them out as well is because we've still got open an open tutorial, certainly on the resistance from resistivity and shape and resistance change with temperature pieces, and the homework is still open. So I'll probably cross most of these off next week for the lecture. In yellow, some of the things I want to try and talk, right? Series circuits, parallel circuits, combination circuits, Kirchhoff's voltage law, Kirchhoff's current law, and voltage and current dividers. Okay. Just a reminder that homework 1 is due this evening, and when I checked yesterday, and that's the wrong way around, isn't it? It's should be February 5th. When I checked yesterday, 15 out of the enrolled 23 people had submitted the homework into Blackboard, so please be aware that that's closing at 11:59 this evening. So have a go doing it today. It's just a multiple choice question, and then next week, two of the homework assignments are due. KCL, KVL, and voltage and current dividers, and then the first lab, which was basically just installing LT Spice, is also due next week. So in today's session, I don't think I'll do it in this order. I think I might talk at you for a little bit first, and then we'll go back to the tutorial, and I'll see if there are any questions about the lab, and we'll look at the background stuff on linear algebra, because when we look at mesh analysis and nodal analysis, that really depends heavily on you being able to use matrices and vectors confidently with to solve them. And there's a couple of questions on that tutorial sheet that I'll probably just go through with you directly rather than splitting up into breakout groups, but we'll see how we go. So does anybody have any questions about what we did last week and anything about what I've just talked about? No? Okay. So
Yeah, I have a question.
yeah, go for it.
So since I'm not in the class officially, so how would I go about like getting the work done? Like, would you keep it up
Well,
there for me?
let's get the paperwork out of the way, Alex, and I can work wonders. I can let you have access to the stuff out of turn. That's easy to do.
Okay, great.
Let's get you officially into the class first.
Yeah, I'm trying to fix that. But
That's
thank
okay.
you though.
You're welcome. It's a no-brainer. Don't worry about it.
All right.
So the other thing I meant to say, and I should have told you about it last week, is Professor Broderick has been working on a textbook for this course, and I've been helping him chip away at it, and it's nowhere near complete yet, but it is there, and it does cover all of the stuff we're talking about in 236. So I haven't made it available in Blackboard yet. I only thought about it relatively recently. So I will make it available in Blackboard. But if you use OneNote, I've made a new open area called reference material, and the Broderick book is there, all however many 191 pages of it. Okay, it's still a little rough, and it's not complete, but it's there, and a lot of the things that I've been talking about are certainly in it, right? There's all the stuff we did last week about, in fact, there's the table I used, right? There's conductance and physical properties, resistance from physical properties, etc. Passive sign convention. The other thing, and one of the things I've helped put together that's actually part of the way this book works, is I like out, and I put together this crib sheet, which is because normally if we're in a normal situation and we have midterms and exams, I allow students to bring in one double-sided sheet of paper with notes. Spent a couple of semesters working with students trying to figure out what should go on those 2 pages of notes for 236. So came up with, and it took about a year or so of fiddling with what should go on it. So it looks a little complicated, but this is a distillation of the whole semester's worth of work, right? So I made that available, and I will make it available also in Blackboard. I haven't done that yet. Let me just write down a task for me to remind myself to put it into Blackboard. Okay, so just if you find the textbooks not doing it for you, or if you find the lecture notes are not doing it for you, it's just another place to look. I don't like talking about the competition, but the other place to look is Khan Academy. They have some really nice videos that go through a lot of the stuff I'm talking about. They don't use the same notation, so sometimes it looks a little different, but it is the same. And I may even refer to some of the videos as we go forward. So let's start. And again, I've forgotten to take the spring 2019 off. And let's think about circuits, right? That's what this course is about. And I can't start with this sentence. Two elements connected in series share one node exclusively. Now, I can't really talk about that without first writing out some definitions, right? If I have a circuit right, and there's a few things we can talk about. So there's a few parts to this. One part is these pieces of the circuit, right? The pieces between the elements, between the components. Right? And these pieces, A, B, and I'll call this other one G. A, B, and G are what I would call a node. And the definition of a node is an area of constant voltage. Okay? So node A, all along that wire, is the same voltage. All along this wire in node B is also a constant voltage, different potential possibly from the voltage at node A. The voltage on node G is constant, and because I've drawn this diagram here, or this circuit element here, means that the voltage at node G is at ground, right? So that's what that, and it means that the voltage there is zero by definition. And that reminds me, I'm going to get you to go out and take a picture for me. And what I want you to take a picture of is a ground rod. Now, you may have heard of the term ground, and you may know that if you have a 3-pin outlet in the wall of your house, that the bottom middle pin is the ground pin. What you may not know is that ground pin has a wire connecting from the thing on the wall of your house, or where you are, to a rather large, surprisingly long, usually copper or brass spike that is driven into the ground. And what you should find, let me just see if I can find some examples. What the assignment is going to be is for you to go out and find one of these, and just about every house has one, every apartment block has at least one. And I want you to go out and take a picture of one of those grounding points. Let me just see if I can find the previous ones. Okay, what I want you to do is something like this, right? Take a picture with something that identifies that you've taken it recently, right? There's another one. That's that one. That one's a bit of a mess. Let's try that one. There we go. Right, so this was done over the summer. Them in the winter with the snow, but what I want you to do, I'll set that up in Blackboard, is go out and have a look for one of those. Anyway, that's a bit of an aside. So one name that I want you to think about is node. That's why so in order to define how circuit elements are in series, I need to define what a node is. So in this case, let's reread the sentence. Two elements connected in series share one node exclusively. Right? So here's a node, and only R1 and R2 are connected to it. So R1 is in series with R2. Okay? And the defining thing about elements being in series is that the same current flows through both of them, right? If we have I1 flowing through R1 and I2 flowing through R2, if R1 and R2 are in series, then we have to have that the currents are equal. And what that means, let's think about that, right? So let's think about, right, we've got the current I1 flowing in through here, and that means if we follow the passive sign convention, we've got the positive side there and the negative side there. If we've got I1 and I2 equal, and we've got the current flowing into the positive side, so we know that across R1 is equal to I, let's call it R1, times R1, just by Ohm's law, right? And we know that the voltage across R2 is also equal to, right, because IR1 and IR2 are equal. So that's the voltages measured there and there. So the question is, what's the voltage measured from there to there? So V total is just equal to VR1 plus VR2. Right? So that means that V total is equal to R1 plus I R1 R2, and we can rewrite that as I R1 outside of R1 plus R. Right? So what this is saying is we can rewrite series resistors as the addition of the two resistances, right? So we can replace series resistors with a single equivalent resistance. Everybody okay with that? Okay, so another quick aside. That is one way to represent the ground node. It's another way to represent the ground or zero voltage node. And that's another way. On why this ground symbol 1 might be used versus ground symbol 2.
The first one, I think that symbol's like Earth because it's like a surface symbol.
Yeah, exactly. So it is like Earth. Sorry, I just noticed somebody can't get on. Let me just, sorry. Yeah, so that's right. So the Earth, right? In fact, if you go to I don't know, if you go to any of the if you go to any of the it's not coming up quickly. If you go to any of the hardware stores, you'll be able to buy a rod. There we go. So this is just at lows, right? And it's a an 8-foot copper rod. And the whole point of that is that 8-foot copper rod is driven into the ground, and that is what gives you your 0 volts. So, anybody got any thoughts about the other one, symbol 2? Let me go with bingo, see if I can call on somebody. Spencer, do you have any thoughts about where a ground or an earth?
I do have a question about the...
Go for it.
So, again, so I work at a company that does a lot of high voltage testing, and we use ground rods quite frequently, but we use temporary ones. And what sort of differences in behaviors would you likely see between having a ground rod that's an earth ground that's like 8 feet down versus only 3?
That's a good question. I think the issue might just be an 8-foot one's not going to move as much, right? An 8-foot one is getting 8 feet into the ground is a bit of a challenge, right? And once it's there, it ain't moving, at least not easily. Whereas a 3-foot one is going to be easier to put in the ground. It's temporary.
Yeah, I wasn't
Yeah.
that length difference would create a difference in electrical property.
Probably not. Not for the. No, I can't think there'd be a huge difference in electrical property, right? The only things I can think of are more real that would be. It. You could probably get away with a 1-foot one if it were only really for the day or something like that. But yeah. So that's cool. That's cool that you. So how long is temporary for the 3-foot ones?
1 day at a time. We have trucks that test power cables up to 60 kilovolts, and
Cool.
drive out to our work site because we have sites all over the country.
Yeah.
So the rod goes in and out.
That'd be interesting. Cool.
Sounds good. So as for the other ground symbol, I have not the one that is a 2 perpendicular lines with the shadows. Number 2, is that what the one that you're asking?
Yeah. This where's my. Yeah, this one
I
here.
haven't seen that in my usage. I would presume that it's ground on a PCB, which generally does not connect straight to earth ground.
That's a good answer. I would call this representation what's called chassis ground, right? And the usual thing I do is several of my former students work at Electric Boat, right? And Marine, you can't have a ground spike, right? But you've still got to have a 0 voltage reference, and so oftentimes the electrical diagrams and everything at Electric Boat don't use the number 1, the earth symbol, because it'd be silly. They use the chassis ground symbol because that's what you've got. You've only got the thing.
Mm-hmm.
So yeah, okay, cool. Thank you. So that's series circuits, and the next one, the next organization is parallel circuits. And again, this is why I needed to define the word node, right? 2 elements are in parallel when they are connected to the same 2 nodes, right? So remember, a node is an area of constant voltage. So there's a node, and then also here's a node as well, right? So there are only 2 nodes in this diagram, but there are 2 resistors connected between those 2 nodes. So these 2, we just say that R1 is in parallel with R2. And sometimes I use the shorthand R1 is in parallel with R2, right? Just 2 parallel lines between R1 and R2. Now this one is a little different, and in this one we've got that we've only got 1 voltage, right? The voltage across R1 has to be the same as the voltage across R2. They're connected between the same 2 nodes. Nodes are areas of constant voltage. So in this instance, VR1 equals VR2. Right, so VR1 equals VR2. Yep, it's not VR2. So, and that means that I1 R1 equals R2. Okay, and then the question is, how do we get an single equivalent resistance from those 2 things? And what we want to do is we want to produce a circuit like that, where we've got an R total and we have an I total. Okay, so how do we do that? Well, let's have a look at it. We know that I total is equal to, now we haven't talked about Kirchhoff's current law yet, but I hope you can think, or you can see that if I have current flow, I total current flowing into this node, and I have IR1 and IR2 flowing, I hope you can see, too crazy to say that I total is equal to IR1 plus IR2. Okay? And then we can think about, well, let's rewrite our let's rewrite that equation in terms of voltage. So the voltage, right, and the voltages are all the same. I total is, using Ohm's law, V total on R total, right? And that equals VR1 on R1 plus VR2, which is also V total, on R2. And then I can cancel out the V totals, and I can get the equation 1 on R total equals 1 on R1 plus 1 on R2. Or rewriting it a little differently, I can say that R total is equal to 1 on R1 plus 1 on R2. Or rewriting it again, I can write that as R1 on R1 plus R2. Top and bottom by R1, multiply top and bottom by R2, and I get the last equation, or the last expression. Okay, so we've got series circuits, we've got parallel circuits. Does everybody understand what's happening there? Okay. So you've got to remember that parallel in the circuit sense doesn't necessarily mean parallel in the geometric sense, right? Remember the definition of parallel circuits, parallel devices, is they're connected between the same two nodes, right? So here's a node, and here's a node. There's only two nodes, and R1 and R2 are connected between the same two nodes, right? So R1 and R2 are in parallel. Just because two devices are geometrically in parallel doesn't mean they're electrically in parallel, right? So for example, here we have R1, R2 and R3. And again, I'll draw the nodes. Here's a node. Here's a node that's different from the other node. And here's a node. Right? And it looks like R1 and R2 are geometrically in parallel. They are. But they're not connected electrically in parallel, right? Because then this node is different from this node. Even though R1 and R3 are connected to the same node here, they're not connected to the same node at the other end. So let's just pull that up and pull that up. Okay. So they're not in parallel electrically. So one of the nice things about being able to recognize series and parallel circuits is that you can take a circuit like this and eventually turn it into a single equivalent resistance. Right? So let's have a go at, I'll just work through this. Right? So if we've got, let's identify the nodes first. Right, so there's a node, and there's a big node down the bottom here. Right. And then there's one here. And there's one here. Right, and the question, or the thing you were trying to find, is that replace all of those resistors with a single equivalent resistance between nodes A and B that is electrically the same. So one thing I didn't tell you about parallel circuits is the same sort of equation works no matter how many items are in parallel, right? So if I have, what is R3, R4 and R5, if I have 5 in parallel, then one on the total equivalent resistance R1 plus one on R2 plus one on R3 plus one on R4 plus one on R5. Or on one on R1 plus one on R2 plus one on R3 plus one on R4 plus one on R5, right? So let's have a look at this circuit. And you can see that here's a node, right? And let's go with green. This is what I would call the reference node. It's not actually identified as a ground, but because it's at the bottom, I tend to think of ground being at the bottom. So let's, right? And what you can see is 3 ohm resistors are all connected between the red and the green nodes, right? So those are in parallel with each other, so their total equivalent resistance is 1 ohm. Okay, so what I can do is I can redraw this circuit by replacing those 3 resistors with a single 1 ohm resistor. So I've got my 5 ohm, I've got my 5 ohm, I've got a 1 ohm, and then I've got a 6 ohm, got my other 6 ohm. Right, so we've got 5, we've got 5, we've got 1, which is the one we just calculated, and we've got a 6 ohm. And now what we can do is we can see that that 5 ohm and the 1 ohm that we just created out of the 3 ohms share exclusively a common node. So now we can say that this 5 ohm and this new 1 ohm are in series. So we just have to add up those 2 resistances, and we can replace those 2 resistors with a single 6 ohm resistor. We can redraw the circuit again. And we have the 2 6 ohms, and now we have a resistor that is combination of the original 5 ohm and the original 3 ohm resistors in parallel. And now we can look at the nodes again, and we can see that there's a node. And again, we've got this node here. Those 3 6 ohm resistors are all connected between the same 2 nodes. Again, I'll use and green for this one. So now we can do the same thing again. Another one on our tot equals 1 on 6 plus 1. So that means that R tot, the second one, is equal to 2 ohms. Right, because 1/6 plus 1/6 plus 1/6 is 3/6, which is 1/2. 1 on 1/2 is 2. So then I can redraw that again. I probably should have thought a bit better about where I draw these things. So let's take it down here. And now I can just write the circuit like this, right? And again, I've got remaining resistors sharing a common node exclusively. So I can say, finally, remember this is B and this is A, I can say that the resistance between A and B is 7 ohms. Right, so now I've taken the original circuit, and I've drawn it, but I've converted it in. What's the picture? Somebody out? Is it cool? Okay. Yes. Does anybody have a? Yeah, go for it.
So I'm looking at the three resistors which are in this in